What is laser? A laser is a device that emits light through a process of optical amplification based on the stimulated emission of electromagnetic radiation. The term laser originated as an acronym for light amplification by stimulated emission of radiation. 2.0 Different type of devices. Type of laser: solid laser, gas laser, dye laser, excimer lasers, semiconductor laser. 2.1 Semiconductor laser. It is also called injection laser, junction laser, or laser diode. The material which often used in semiconductor laser is the gallium arsenide. The emitted radiation from semiconductor laser is highly monochromatic and produces a highly directional beam of light. 2.2 Why semiconductor lasers differ from other lasers. 1. In conventional lasers, the quantum transitions occur between discrete atomic energy levels, whereas in semiconductor lasers the transitions are associated with the band properties of materials. 2. A semiconductor laser is very compact in size, on the order of 0.1 mm long for discrete lasers. 3. The spatial and spectral characteristics of a semiconductor laser are strongly influenced by the properties of the junction medium, such as band gap and refractive index variations. 4. The laser action is pumped simply by passing a forward current through the diode, as opposed to optical pumping, for example. 3.0 How diode lasers make light. The part that we are most interested in is the laser diode. Let's have a closer look at it and see how it produces laser light. I will now make a section through the laser diode. A typical laser diode consists of two semiconductor, one sandwiched above the other. On top is gallium arsenide, a compound that has been engineered to have holes in it that it would like to have filled by an electron. Semiconductors that would like to gain an extra electron are referred to as p-type semiconductors. On the bottom is gallium arsenide and selenium. This means it now has an extra electron that it would like to lose. Material with an extra electron is referred to as an n-type semiconductor. When p-type and n-type semiconductor are put together like this, you create what is called a p-n junction where both materials meet. When a current is passed through the semiconductors, both the negatively charged electron and positively charged holes begin to flow towards the p-n junction. The electron from the n-type semiconductor and the hole from the p-type semiconductor combine. However, because the hole exists at a lower energy level than the free electron, the electron must lose a small amount of energy to combine with the hole. It does this by releasing a single photon of light. The top and bottom surfaces of the p-n junction have been coated with a mirrored material to trap the photon light. The photon bounces around inside the p-n junction on the mirrored top and bottom surfaces. This photon encourages other holes and electrons to combine, and they also release their own photon of light. The released photon will be the same phase, polarization, and go in the same direction as the original photon. This process will continue and more photons of the same phase, polarization, and direction will be created. The photon will keep increasing in numbers until the whole p-n junction is filled with laser light. Some of the laser light exits the rear of the laser diode and hits the photodiode. The photodiode uses this information to regulate the voltage to the laser diode. The vast majority of the light exists through the front of the laser diode. As you can see, it is wildly diffracted, i.e. splaying outwards. This diffracted light must be made into a typical straight laser beam. This is done by passing the light through a collimating lens. 4.0 Energy Band Diagram. Figure 1. Energy versus momentum. For a semiconductor with a direct band gap. 1. All semiconductor lasers are used direct band gap material. 2. The band gap is called direct if the momentum of electrons and holes is the same in both the conduction band and the valence band. An electron can directly emit a photon. Figure 2 is energy band diagram of laser diode under thermal equilibrium. Figure 2 shows a p-n homojunction laser that has the same material or XGAAS on both sides of the junction. Figure 3 show an energy band diagram of laser diode. When forward biased. 1. The dominant process for semiconductor lasers operation is stimulated emission. 2. When forward voltage is applied, electrons are injected from the N region and the holes from the P region into the space charge region. 3. When a sufficiently large voltage is applied, high injection occurs, that is, there is a large concentration of electrons in the conduction band and the holes in the valence band in the space charge region. 4. This is the condition of population inversion as shown in Figure 2. .0 Performance parameter. Optical gain. Most important parameters relating the physical properties of the semiconductor structure to output characteristics of the laser diode. Optical gain and its dependence on the operating conditions determine not only the basic output characteristics, such as threshold current, but also the temperature dependence of the output characteristics, as well high-speed performance of the laser. Optical loss. Internal optical loss is a fundamental characteristic of a semiconductor laser. It is an important parameter because the value of internal loss affects threshold current and external slope efficiency. The optical loss has a number of different contributions. Most important among them are the free carrier, intraband, absorption 29 and scattering loss on the waveguide. No uniformities. Line width enhancement factor. Line width enhancement factor ED is a critical parameter determining both the static line width of the semiconductor laser and instantaneous wavelength change of the semiconductor laser under direct modulation. Determination of the parameter is therefore important for understanding and improving the laser design and performance. 6.0 Efficiency. Figure 4 show a typical light versus current curve associated with a high-power laser diode. Threshold current. 1. As the injected current is increased, the laser first demonstrates spontaneous emission that increases very gradually until it begins to emit stimulated radiation, which is the onset of laser action. 2. This generates the output light versus input current curve, more commonly referred to as the Li curve shown in figure 4. 3. This is typically referred to as the threshold current and is denoted by the symbol if. 4. It is generally desirable that the threshold current be as low as possible, resulting in a more efficient device. 5. Thus, a threshold current is one measure used to quantify the performance of a laser diode. Threshold current density. One threshold current density is denoted by the symbol JTH and is determined by dividing the experimentally obtained threshold current value if by the area of the laser. 2. It is always desirable for a laser to have a low threshold current density value. 3. Threshold current density is one of the parameters that is a direct indication of the quality of the semiconductor material from which the device is fabricated. 7.0 Example application of laser. Semiconductor lasers are used in 1. Optical communication. For example, the portable optical telephone and multi-channel stationary communication lines. 2. Optical detection and ranging and special automation systems, such as range finding, athymetry, and automatic tracking systems. 3. Optical electronics, for example, the emitter in an optron, logic circuits, address devices, and holographic memory systems. 8.0 Islamization part. Science and Al-Quran. Have you ever wondered why human cannot see jinns? This can be explained by using electromagnetic radiation spectrum.
أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم.
والجان خلقناه من قبل من نار السموم.
1. Every object emits radiation. 2. The conventional light which is visible to us occupies a very narrow band of the electromagnetic radiation spectrum. 3. We humans cannot see an object if the wavelength of its emitted radiation is below or above the visible light range. Refer Figure 5.